Hello, everybody. Good morning, good evening, good afternoon, and welcome to our newest episode of Going Meta. It's episode number 6 in season 3. And since I've heard last time when I wasn't there that my intro was a little bit lacking, I like to introduce everybody to Jesus Barraza, graph data modeling legend and semantic expert and enthusiast, I guess, and the person who now with me, but my contributions I think are a little bit limited in this case. But Jesus is the person who makes ontology discussions feel like a fun discussion, fun adventure, and not like a boring, dry philosophy lecture. So I'm really excited to have you join me again, everybody else again, for this newest episode of Going Meta. And the topic is validating Neo4j graphs with SHACL. So that should be fun and exciting, interesting. We talked about SHACL a couple of times before. It's been on our radar, or in this series it was mentioned a couple of times. So this time with validating graphs.
That's right. Well, thank you very much, Alex. And I have to say that I'm loving this kind of competition to see what next time is going to be on me. But yeah, I have to say that it caught me completely off guard. The intro. I don't know if you've listened to it that Adam came up with. That was fun. But it's good to have you back. I hope you enjoyed your break.
And, yes, I did. Yeah.
And so we're coming back to one of our. I wouldn't say our favorite topics, but one of the loved topics that we've touched several times, and it's kind of revisited, in a new perspective. But at the core is actually an essential element that also goes very well with our Going Meta series, because it combines all these ideas from the two graph stacks, from the semantic stack and property graphs and it's and it's an important element. Data quality, graph validation is something that any graph user cares about, and I'm looking forward to spending a few minutes talking about it, and not only talking but always doing things with it and playing with it, and sharing with our audience. So yeah, looking forward to this.
Yeah, looking forward to it as well. And like you said, discussion exchange is always important. So if you have any questions while watching this live, use the chat. I will see your messages. I see your questions or comments, so we can read those and cover them. If you have any other questions later on after you watched this episode, or where you wasn't able to watch it live and you wanted to have a question or comment, and use YouTube. That's the best way. YouTube comment underneath the latest episode. We look at that as well, and we try to incorporate either your suggestions to one of the future episodes, or at least we cover answer the question that you might have raised. So that's the best way forward. And here we are.
Excellent. So I see my screen. Slides. My desktop is already up there. So yeah, let's get going. So as always, I'm going to take a moment with some slides to give some context and to frame the subject, and then we'll jump into code and into graphs. So yeah, the topic is validating Neo4j graphs with SHACL. And like you said, this is a topic that we've tackled a couple of times. It's crazy that it was a while ago. It was April 22 and January 23. So if you want to go and watch our younger Alex and younger Jesus, go. But so it's like all the episodes, you'll find them in our GitHub repo. But don't worry, because I'm going to take a moment to give you the context, and to for those of you who are new to these, We'll cover that for you. So let's start always with the why. Why do we do this? What's the problem that we're solving? And what we want to do is we want to basically control the quality of our graph, right? And what that means is we want to detect quality issues, and we'll see that they can be of many different natures. So they can be structural features. So are things connected in the right way? Are the cardinalities the right one? Are the types of the nodes being connected? Or they can be value related. Is that property of the right type, or does it have the right value, etc., etc.? So I want to detect this kind of issues, which I could do by writing Cypher queries, but I want to do it without writing Cypher. I don't want to write custom code. I want to do it in a declarative way, as we've referred to a few times. So I want to describe what my graph should look like, and I want something else to take care of translating that into something actionable, into some Cypher queries, but without me having to rewrite them. So what I want to do is make my life simpler as a kind of data owner, as a data engineer in this case, and that's just to give some examples of the kind of things that we might want to do. What do I mean by these kind of data quality issues? I want to be able to enforce, for example, that a customer's phone number aligns with a particular regular expression, so it's form of numbers or prefixes or whatever, right? So I want to describe that in a way that then it's applicable to my graph. I want to, for example, be able to express that a product node must be connected to at least 3 supplier nodes. And you might notice that this one kind of extends the problem statement, right? Because these could be considered a data quality issue, but it's kind of a business rule, right? Let's say that what we're capturing here is, in order to be to have the resiliency required to be able to supply a product to our customers, we want to make sure that at least we have 3 suppliers. That's not really quality, is a business rule. And we're going to see that the same formalism that we're going to be using today can be applied to exactly that, because ultimately what you're going to be doing is describing patterns that should be verified in the graph. Some of them will be probably more lower level, like data quality issues, but some of them might be, more advanced and more related to the business. But it's another example, something like, hey, a supplier must have exactly one name and not more than one, right? So these sort of things, and or for example, that an order must contain properties within a particular defined collection, but not outside that. So in a way, what we're doing, what we're going to be doing, is kind of putting guardrails or controlling the flexibility that for example Neo4j gives us, right? In Neo, you can be pretty flexible from the point of view that I create a person node with a name and a date of birth, and the next one has a name but doesn't have a date of birth, and maybe has a nationality or whatever. So this flexibility is built into the property graph model, which is great. I mean, that helps you, especially in the development phase, to move quickly, to adjust, and to iterate. But at some point, you might want to introduce some kind of structure, some kind of rigor, some kind of discipline. And the way to do it is exactly what we're going to be discussing today. So that's the problem that we're addressing. Does that make sense, Alex?
Yeah, that makes perfect sense. Yeah, I think it's interesting what you mentioned. Like you talked about, okay, data quality up to business rules, and we cover a bit. And you think, okay, this is this one side of the house. Once you get this done, everything else follows. But you have to look at both sides, and you have to make sure that, of course, data quality is important, but also these business rules are important, and you can weave them all into a graph, and that's very interesting.
Yeah, totally. And the same formalism, the same mechanism, the same technical approach that we're going to be using, maybe at different stages in your process, whether it's a data ingestion, might be, like you say, data quality. I want to make sure that there's no incorrect or data that diverges from the expected shapes. But then later on, it can be something that's controlled, or that's used as more of a business monitoring rather than data quality. But yeah, these are ways and of course, as always, I'd love to hear what our audience and our practitioners think of it, and how would they would they use it. So yeah. So we mentioned SHACL in the title, and that's what we're going to be using. So SHACL, for those of you who are hearing this for the first time, is a W3C standard, a recommendation language for defining constraints over a graph. So we're going to see what this looks like in detail, but you have the link there if you want to have a look, and it's a pretty rich language to define the kind of things that we just described. So why reinvent the wheel if there's already a language that exists out there? And like many others, we've talked about SHACL, but we've also talked about OWL and RDFS. Remember that these standards defined by the W3C are by definition, like ontologies, right, are declarative and are formal knowledge constructs that are meant to be translated into something actionable. That's what they're formal. Like, we can parse them, we can do things. And you have a whole series of episodes, 40, 50 of them, where you can see how we've done that, right? So we used an ontology to drive the construction of a graph through the automatic creation of a data ingestion pipeline. The same for the retrieval, the same for entity extraction. So this is exactly the same. So we're going to formalize this definition using this W3C standard, and we're going to apply it, because that's the way it's defined. So this defines the what, but not the how. So that's what we're going to be implementing ourselves, is how these applies to our graph. And in order to see how that does apply to a graph in Neo4j, let's try to understand what's in a SHACL shape. And I hope this is readable. So first of all, SHACL shapes are defined using RDF. Let's not worry too much about that. But the idea is the vocabulary is very much defined in terms of nodes and relationships, right? So what you will see is, well, there's a bunch of prefixes. Everything in RDF, is defined by URIs. So we'll define prefixes. Let's skip that for now. Let's not worry too much about it. But we will see that the definition of the shapes are called node shapes. So basically what we're describing is what's the structure, what should be the shape of a node. And you will see that there is a definition of a node shape, and you would describe to which class, to which category, to which label that description applies. So basically what we're doing here is we're describing what the nodes of type product would look like. And we will provide a number of detailed descriptions of what their properties of the relationship should be like. In the first case, we'll see that there's a bunch of properties. So you see that there's property elements. In this language, property is a general term that's used for both what they call object properties, which is relationships in Neo4j, or data type properties, which is properties, attributes in Neo4j. But the idea is that here I'm defining, for example, the property called product name. And I say that the product name has to follow a particular pattern, or in other words, a regular expression. So this is a kind of a constraint, a rule, where I'm saying that the product name, the value of the property product name of product nodes, has to verify this regular expression. There's an additional one that we can only have one, so it cannot be a multi-valued property. In Neo4j, you can have property values that are arrays. But in this case, even if it's an array would be valid as long as it has a single value. So the thing is, the cardinality, we cannot have more than one in this case. This is the maximum. We could have 0 because we're only setting the max. So in this case, we could have declaring it as optional in a way. And also we're saying that the data type is a string. So this is pretty straightforward and easy to understand. We're doing something similar with the unit price. Unit price is another property, and we're saying that we can only have one, and it has to be between 10 and 100, right? So the minimum and the maximum, exclusive in this case. And the same with relationships. So relationship supplied by connects a product to the supplier. So we're specifying two things: that at the other end of that relationship, there has to be a supplier, and that the cardinality has to be at least 2. That's something like we were describing before. So for every product, we need at least 2 suppliers. So, I mean, I don't expect people to come out of this, as fully experts in SHACL, but we kind of get the idea of what's there, right? So it's a collection of property constraints and relationship constraints grouped by label or by type, by category. That's pretty much it. So now the thing is, people would be saying, okay, that's fine, but you don't expect me to write that, and these days even less, right? So now that no one writes code and that we have LLMs helping us, so yes, I mean, of course, if you have something like that, or if you have a tool that produces that, and we have to think that, like always, Alex, we're working with people that probably combine Neo4j with tools from the RDF stack. Maybe you have and I have not done my research on that side. We've used a lot of Protege here for editing ontologies, but I haven't found a tool that would help you editing SHACL. Maybe there's one there, but anyway, let's assume that we have this SHACL, and whether you've written it, an LLM has written it for you, or you've created it with some tool, we will start from there. But if you don't want to write it yourself, we also and that's something that we covered, remember, right, in January 23. We created a library, a Python package that gave you an option of defining these sort of constraints in a Pythonic way. So instead of you writing this RDF-based syntax, which for some people might be a bit arcane, we created a bunch of, a package that would let you do things like, well, I'm going to define a company, and for the company, I'm going to specify that I want the property to have values of a particular type. So it's very verbose, but quite intuitive, right? And more Pythonic than what we saw there. And then once you create that as a Python object, you can serialize it and get the RDF version of it. So you're still creating the SHACL. So under the hood, there's the SHACL, but you don't have to write it yourself. And just since we're going to see it in a minute, I would say that the way you organize things, and you will see how it aligns to the description that we saw a minute ago. What we'll do is we'll define sets, as in a set is a collection of nodes that I'm going to constrain. So I would say, well, I'm going to define constraints for the set defined by the label company. So I can define a set by nodes of type company or nodes of type customer or whatever. But sometimes I might want to define sets not by a label, but by a richer expression that can be a Cypher expression. So in this case, maybe I'm looking for nodes that are located in a particular city, and they can be customers, but they can be providers, or they can be suppliers or whatever. As long as they're based in the Americas, I want to define a constraint for them, for example, right? So that gives us additional flexibility, because sometimes you want to define the constraint, just associated to a label like we've seen, but sometimes to a set of nodes defined by a rule, like a query in this case. So basically, this is, as you can see, is the equivalent of what we saw a minute ago, like a node shape. So what we're defining is a node shape, and then we will extend it by adding properties, property constraints, like we've seen, and then we'll bundle them all into what we call a suite. So a suite is a collection of sets. So we would define, okay, there's a suite of all the expectations, all the, we call this package graph expectations, because in a way you're kind of setting the what you expect your graph to look like, and we bundle them, and we add to the suite all the expectations that we've created, and that would be like something like the company expectations, like your customer, your location, etc., etc. We'll see that in code in a minute, but basically this is, like I say, it's a programmatic way of generating this SHACL that sometimes we may not want to generate by hand, but any other approach is equally valid. So does that make sense? I mean, is that enough of an introduction to go and try it?
No, that's very cool, and that's a nice throwback to, and I looked it up just now, episode 11 of Going Meta, where we talked about graph expectations.
Exactly.
And I think that's been a very fun episode. So I'll link it in the video description. So if you want to look back in time and see what we did back then with graph expectations, take a look at that. I liked it. It was a nice.
I think
nice way.
So, and you probably remember, if you go watch that episode, the graph expectations package makes it possible for us to define, as we're going to see, the shapes, like the constraints that I want to apply to my graph. But I could also bind it to a graph, and but it relied on the fact that the graph had Semantics installed. You probably remember that Semantic had an implementation of SHACL. And now we no longer have this assumption, because Semantics is not always available, and specifically in Aura deployments, it's not available. So that's why what we're showing today is kind of an entirely client-based approach. So it's fundamentally the same, which shows again, this idea that a SHACL definition or an ontology or a declarative definition of some semantics should be, actionable in as many ways as we want, as long as it complies with the definition, right? And that's exactly what we're doing. So what we have now is yet another implementation that will make it work on any Neo4j instance, because it kind of takes away the this kind of translation of SHACL into Cypher rules. So So yeah, what we have is I have my Aura instance here. So that's my database, which I've populated. Let me show you a little bit of what's in there. So I've populated it with the Northwind database. So we have something like customers. Well, let's start with orders. So if we look at orders, I hope this is readable. Maybe I want to make it a bit bigger, right, Alex?
I think a little, yeah, that otherwise I may need to zoom in, but I think that, yeah, no, it's good.
So if I actually, let me build a richer pattern. So an order will be connected to the customer that places it. So it's purchased. I think that connects it to a customer, if I remember correctly. Customer. Let's see. Or instead of getting these, I'm going to get the whole subgraph SG. Let's return 3 of them. And yeah, we have at the center we have a customer that has purchased 3 orders, and we can keep expanding, and we'll see that the order actually has I believe it's an order for a product. So it connects the order to the product, and I think it's includes or something like that. Or what was it?
Part of?
Part of, maybe? No, I think it's orders. I mean, the naming is a bit funny.
Yeah.
There you go. So it's orders. I mean, I don't love this particular schema because it's not. But you see that how a customer purchases an order, I would say places an order, right? And the order includes some products. But anyway, let's not get into that. But that's what the graph looks like. So we have the customer, the order itself with the details about the order. The order has information about the items, the number of items of a particular product. And I think lastly, there was a link between products and suppliers. So for every product, there's a supplier that I suppose supplies a product. So something like that. There you go. So these would be the complete graphs, right? So now we have 3 customer orders converging on the same product that's supplied by a particular supplier. There you go. So, well, that's the graph. Like I say, if you go to your desktop, if you're on desktop and you do play Northwind, you should be able to populate this graph, and it's a pretty straightforward one. Okay, so that's the data the graph that we're going to be working with. And now we're going to show the code. So let's make these a bit bigger. Or is it readable? You tell me, Alex.
This looks good now. Yeah.
Good. So the first thing is I'm going to install the packages, right? And as you can see, I'm not doing a pip install directly. I'm loading them from the test PyPy environment, because we still have not deployed them. We have them in test mode, but anyone can do that. They're there for sort of in pre-release mode, so people can check them out. So once we have the installation done, I would show how the creation of these shapes can be done with the graph expectation package. So I will I will import the graph expectation object, and what I do, like we saw before, is we're going to be creating, I'm going to create a set to define, the shapes or the constraints around my suppliers, right? So supplier, as you can remember, is one of the types of nodes in my graph, right? So you see that exotic liquids is one example of it. And for suppliers, I have things like the address, the city, the company name, etc., right? So I'm going to define some constraints for it. And since I don't want to go and write the SHACL directly, what I'm going to do is use this library and say, okay, I create a new set that applies to nodes of type supplier. That creates my expectation, my supplier expectations. And the first rule, and you will see that, once I create the variable, so I can say supplier expectations. And when I do dot, I can type expect, and it gives me the whole menu of things that I can use. I can say, that a particular key is a property, that something is a relationship, that a node type has to be in a list, that a node type has to not be in a list. So it's a bit verbose, but it's very intuitive, right? So I can say, I don't want my node. I mean, I don't want a supplier to also be a customer. That would be a violation. So I want to exclude. That's what these predicate would be for. I can describe the number of incoming relationships of a particular type, the number of outgoing relationships. Well, anyway, a very rich catalog of shapes, but done in this kind of more Pythonic way. And an example of that, as we see here, is I'm saying that the property, I expect my property values to match a particular regular expression. And I'm referring to property country. And I expect my country to be basically something described by letters, and not contain things like numbers and stuff like that. That's the typical data quality validation, right? So I would say, and well, then what I can do is I can associate a message, some information or some severity associated with it, then will make it possible for me, when I run it against my graph and detect violations of these, I can refer to the rule that's being violated. So I can be descriptive about it. So here I'm calling it rule number 1. If this gets violated, it means that it's an invalid country, right? I could go on and say, for example, there's another expectation on my suppliers that the number of incoming relationships have to be between, in this case, I'm setting the minimum, not the maximum, but basically I'm saying that the supplied by relationship, which is actually incorrect because it's supplies and it's outgoing. So let's fix that. So is the number, expect a number of outgoing relationship to be between 2, for example, and the name of the relationship, like we saw, is supplies in capitals. So it's not this. Supplies is outgoing, and the minimum I'm specifying that it's 2. Well, let's actually say 1. If I said 2, no one is going to verify that. But anyway, let's put 1, and I call this. Let's set it to 2, even if it generates a number of violations. So, okay, before I go any further, so this is the approach that this package takes, right? So if I do that and I create my expectations, and all I do then is I add them to a suite. So because I've only created this one, I'm going to comment out the rest, and I'm going to add to my suite. Oops, I need to close the bracket. So I have my suite. And I can go ahead and print it. So it generates the SHACL for me, right? Which is easy.
Nice.
So I don't need to go write it, but this is valid RDF. And all I have to do now is go and run this against my graph. So that's what we're going to do next. So this is the generation part, and we'll go into, well, we may or may not want to go in detail, but basically you see how this would extend, right? So I now want to add constraints for product, right? And I define a new set, which is for product. I want again specify that the number of property values have to be, and this is the unit price. This is a specific property. I want the unit price to be between 1 and 1, which is have exactly one single value. So things will have a single price. So I'm specifying there that the cardinality for this relationship has to be exactly 1. And then I'm saying that the property values have to be in a particular range. So the unit price has to be unique. But it also, in addition to being unique, has to be between 10 and 500 because my products are in that particular price range. And I call this price limit. So I keep adding constraints and giving them aliases there so that I can then run it against it. And all I have to do is, well, since I've added a new product expectation, in this case, I keep adding it to my suite. And if I extend my suite with this one, if I now generate my SHACL, it will have the product, but it will also have the suppliers, right? So, and like this, we basically work around the problem of having to write this SHACL by hand. But pick your tool. If you want to use graph expectations, you can. If you want to use an LLM, make sure that it generates valid code. But that would be also a good approach. I mean, the good thing about this is, like I was saying before, is that now I can go and just like I did with my ontologies, this is something that I can serialize, that I can track over time. I can go to GitHub and check it in and see how it changes over time, version control, build it into my software development cycle. So lifetime, and it's basically an artifact that helps me defining my data quality rules or my business rules and build them into my, in this case, probably data ingestion workflows. So part one, generation of these SHACL. That's one option. Now we have the SHACL, right? And this is kind of a more complete version. I'm going to, well, it's a bit longer, but it's just an extension of what we just saw, right? So we have a node shape here that is product, and I'm specifying. I'll go a little bit into the details, but it's meant to be a bit more readable, but it's exactly generated in the same way. I have shapes for products, I have shapes for customers, I have shapes for suppliers, and I have just one for a subset of products that are supplied by suppliers in the US. So this would be a subset of suppliers, but applicable to the USA. And just to show how we can be super expressive and specify constraints that apply to not necessarily only labels, but maybe specific, very specific subsets defined by whatever logic I want to include, right? So this is what this extension is doing. And this, by the way, this target query is an extension to the formal SHACL, right? So if you process that in a RDF-based system, probably this will be ignored, but this is quite relevant and quite useful, and we use it a lot in Neo4j.
So this, what you just showed here, is this another set of rules now, or is this
yeah, I mean, it's
else?
kind of it's sort of an it's an extension of this one, right?
Yeah, okay.
But I put it in a more nice, readable, hopefully a bit more readable form. But it's the same. Okay. It's the result of generating either through graph expectations, or maybe if you are comfortable writing it by hand, you can. The good thing about SHACL, it's a standard. So as long as you comply with the standard, it doesn't matter where it comes from. We'll be able to process it, and it will work on your Neo4j graph.
Okay.
So we have this collection of shapes, right? And what we're going to do is, well, basically run them against our graph. And what the code, and I'll go in a bit more detail, is pretty straightforward. So we've installed the package before, so now we have this shapes validation package, and we are going to create two objects, right? The graph configuration, which is basically a way to connect to my Aura instance or to my Neo4j deployment, and then the validation client. So that's what I'm doing here. So I create a Neo4j driver. So that's the usual thing. So you would create, this is the Neo4j driver. So I create a connection to my my URL, in this case, is my Aura instance. I'm pointing to this database that I showed a minute ago. And I provide the authentication, right? In this case, I have it in my secrets here in my Colab notebook, but it's provided in the usual way. So I create a driver and verify connectivity. And all I do now is I create an instance of this validation client. All I'm passing is the config, which is basically this driver connection. And I'm setting some basic configuration. And I won't go into details now. Let's assume that these are the default behavior. There were a bunch of ways in which this could operate. You remember how Semantics could import RDF data into Neo4j, and still can, of course. But you have different options, whether you wanted to preserve some of the namespaces, so sometimes you wanted to ignore them. Well, I don't want to overcomplicate too many things here. Let's assume that we're working on a purely Neo4j graph like this one. So there's no traces of RDF, which is fine for this example. And that's what I'm doing by setting these default settings. So all I'm going to do is step number one is I'm going to run an import step. So I'm going to tell my client to go and import the SHACL shapes. And I'm passing as parameter the shapes themselves. So this is the text, the serialization of my shapes. In this case, this code here, the SHACL itself. But it could have been, the one generated by the graph expectations. So I know I've kind of cut it in two parts. So if it comes from graph expectations, absolutely fine. But I don't want to assume that everyone is going to generate them using graph expectations. So what's important is that the shapes are defined using SHACL. So we parse them, right, with this import step, and then once we have them, I will have a print step where I say that this is the shapes that have been imported. And what I'm going to do, this is commented out intentionally. I'll get back to it in a moment. I'm going to run the validation. I'm going to say go and validate the graph, and then it will connect to the Aura instance. In this case, it will run the generated cipher to verify that these rules are or are not followed, and it will produce a report, and then we'll show what the report looks like. So if I run that, it should be pretty quick and straightforward. There's a number of warnings, and at the moment it's a bit verbose, but basically what matters here is that we've loaded 9 constraints, which is basically what I passed, and the conformity of the graph is false.
Yeah.
I mean, it didn't pass. There's violations, and we'll go into the details. All these warnings have to do with the cipher that's generated behind the scenes. And there's a number of things at the moment, like, we're using, and it's not critical, but we use node IDs, which is a deprecated feature. So we should be using the longer version of it. But yeah, again, let's ignore that for now. It's kind of a minor issue that we'll probably fix in future versions, but it's just a warning that we can ignore for now. What matters is that the validation has failed. I mean, the graph does not conform to the shapes, and we will want to know more of what's happened. And in order to present it in a nice way, what I'm going to do, remember that the result of the validation is stored in this report, and all we've shown is, the summary, whether it conforms or not. What I want to know is exactly the details. I'm going to load that in a pandas data frame and present it in a nice way. So all I'm doing here, these are pandas settings just to make it look nice. And I'm passing the report, the rows in the report, which are the detailed results. I'm passing it to a data frame and I'm displaying it. So if I run that, it's going to produce a table version of all the issues that have been found in the graph.
Oh, that's good.
So now we can go have a look at that in more detail. And we see a bunch of them, so we can analyze them in detail. But the explanation that we'll see is, okay, there's a type of violation, which is a value range constraint, and it applies to a particular node, and that's where we identify nodes by IDs. This is kind of a deprecated feature.
Yeah.
We'll get to the... But basically, that gives me a way of identifying the node in question. And what happens here is that this node has a property called unit price that's violating these constraint, right? And this is the actual offending value. Exactly. So that's so if we go to the R004 price limit, you remember that we said let's go here. R004 price limit is this first one where we specified that the minimum price for a product had to be 10 units, whatever. We're not using any particular currency, but let's say these are dollars or whatever. So between 10 and 500. Sorry. So you're right. The product in question is too cheap, so it doesn't comply with this constraint, and that's what we're having this message raised. So we can verify, like I was saying, that the element in question, in this case, we can look it up by node ID. So we could go and inspect that. So we can do, and you will see that, there you go. So we get, which was the ID?
12.
12. Number 12. Yeah. There you go. So 12. And the Aura is telling us that these, there you go. So the function ID, you see it down there, is deprecated, and we should be using element ID. So that's the kind of thing that we need to fix. But for now, it sort of works, and so we can ignore it for now. So if we return this node, we see that effectively this product has a price of 6. Which basically violates the constraint that we had defined. So, right. So that's the kind of end-to-end story, right? So you get a summary of all the, and of course, if we can see how this works dynamically. I didn't have to generate the cipher. We'll get to that in a moment, but it works dynamically in the sense that, well, we see a bunch of them that are let's see, in violation of this rule, let's change the limit so that we only get a reduced set. So if I go and change my constraint to say, okay, I'm going to allow prices between instead of 10 and 500, let's do between 5 and 500, right? So that should reduce the number of violations. So I update my shapes.
Yep.
I reload them again and recompile them into Cypher, and we rerun them against the graph. It takes only a few seconds, and now we can produce again the summary. So we will see that hopefully now we have a lot less of them. So we only have the two outliers at 2.5 and 4.5, but we see how the rule has been adjusted, and it's entirely dynamic. So all I have to describe is the what. That's the declarative nature of this approach. So I describe the what, how it should behave, and I delegate to this clever library called validation to translate that into the relevant cipher, apply it to my graph, and give me a summary of the execution. Like this, there's many others, and I think it's worth spending a minute on these particular ones. So this is low product offering. That's an interesting one because it uses one feature that's called inverse. Let's look at that. So if we and this is kind of the expressivity of the let's see here of SHACL. So what we're doing here is we're specifying the following, still within products. So we are specifying constraints for products. And what I'm saying is that, okay, there's sometimes we want to define as part of the constraints for a node things on relationships that are incoming, and that could be, well, eventually if it connects in this case an order to a product, should this be defined on the order side or on the product side? So you will, depending on the rule, it will make sense one or the other. In this case, I want to specify that no product should have less than 2 suppliers. So this is the idea that I was describing before, right? So this would be one that, in my opinion, will fall more under the kind of business rule, right? That data quality one. So what I'm saying is that my product offering is at risk because I'm relying only on a single supplier, right? So I want to have at least 2 of them. So, well, again, same sort of syntax. So I'm saying there's a path that includes an inverse traversal. That's the interesting thing, because if you remember, if I start from product and I go following the supplies relationship, so this is a product. If I expand, oops, there's a maybe I won't, hang on, let me do that in a different way. Let's go to this one. So if we have a product, so the no, we were looking at, suppliers, that's it. So if I start from product, the supplies relationship is incoming, right? Yep. So as opposed to outgoing, and that connects us to the supplier. Yep. So what I'm doing here by defining this rule is I start from my product, which is the node the node shapes that I'm describing, and I'm saying, well, navigate out supplies relationship, but keep in mind that it's an inverse path because the relationship is incoming. Yep. That's what I'm saying here, and I want to specify that the minimum count is 2. So, and it's important to be able to define it from the product side because the cardinality is relevant to a product. I want to say that a product has to be supplied by at least 2. If I was to define it on the supplier side, I couldn't, right?
No, yeah, you're right.
What if the supplier provides a bunch of products? I mean, what I want to do is that any given product is supplied by at least. So that's why it's important, this level of expressivity. And sometimes you will want to use this inverse path approach. Anyway, this translates again into some cipher behind the scenes. And if that gets violated, well, I will be flagging it as low product offering. And that's exactly what's happening in a bunch of them, probably most of them, but I use it just as an example. Yeah. So if I take any of the products in this list, I will verify that the path and this tick indicates that it's kind of inverse. So the supplies relationship is violating the low product offering rule. And we can confirm that that is the case. If we take, for example, number 4, and we can do that. So we know that this is a product, and we want to identify all the suppliers that this product is connected to. right? So actually, I know that the relationship is supplies, but I could have done. So if I get my, instead of n, I'm going to get my subgraph. So I'm going to get all the suppliers that are there for my node. And the node we said it was, which one? Number 4, for example. So I'm going to use 4. So I'm looking at which is the product identified by 4, which is the way I'm identifying the violations, and which are the suppliers. So if I run this query, I see that effectively this product is only supplied by one single supplier, which is effectively a violation of what my rule was defining, which was basically expressing that we need at least 2. That would be the minimum. If I turn this down to 1, which effectively, would be a very not very useful rule, we'll see that if I rerun all these violations will go away, and now we have no longer the low supply, or whatever the name of the rule was. So yeah, the behavior is entirely dynamic.
Yeah.
And it's, I have all the information in my summary to be able to go back to the to the root cause of the problem, basically. So, well, that's the end-to-end thing. But what happens behind the scenes, and that's the last bit that I want to show. And like I mentioned, we have this declarative definition of my constraints in SHACL, and in order to make them actionable in my graph, there's a translation into Cypher happening. So this process is entirely transparent, and at any point, once I've processed my my Cypher, what I can do, my SHACL, and I've compiled it into my executable client, what I can do is, okay, check out all the Cypher that's been generated. So I can see that once the client has been created right here, and the SHACL has been imported, what I can do is, okay, now iterate over all the Cypher generated, and I use this view Cypher function that will give me an iterator, like a collection of all the Cypher bits that have been generated, and I'm going to print them on the screen so that we can see what's happening. But if I run this, so we see that there's a whole bunch of Cypher statements that are being that have been generated, and that dynamically capture, the query that would identify any kind of violation of these rules. So this is entirely transparent, and again, you can find what's happening behind the scenes. And actually, there's something that I don't need. This is just a debug thing that I can remove. But anyway, that's minor detail. So here's the kind of query that we can see that in this case, we can even analyze it in a little, and you could even run them, right? So that's something that you can go copy and paste on the other side. But this one is the range in the value of the unit price. So this is basically the translation into Cypher of the constraint that defines that the unit price has to be in the range between 5 and 500, right? So what would that look like? So what that would look like is I would go and match all the products in my database, because that applies to nodes of type product.
Yep.
And it will get the unit price property, and we'll store it as well. We give an alias of v, and what we would do is, there's several options. If v is null, right, then we will need to understand if that's an issue or not, or if not, we will get the value, right, to understand if it's multi-valued. If it's if the value type function in Cypher will return the type of the value in this of this property. If it's a list, then it's potentially multi-valued. And what we do is that for every value in this list, we have to check, because we cannot anticipate if it's going to be single-valued, multi-valued. It's going to check that the value in question, it's not outside the range. So it's not, between the, it's greater than the minimum, and it's smaller or lower than the maximum. I mean, I don't expect people to go and inspect the Cypher. I mean, this is tested and it's correct. But what I mean, it's entirely transparent and basically produces a summary in case there's a violation of this, of what's the detail of that. And that's exactly what's produced at the end and reported at the end. So this is there as an option. So you can you can check that that Cypher if that's of interest or for debugging purposes. And that's pretty much it. I mean, the other thing that I wanted to show is that sometimes, well, in this case, we've validated the whole graph, so we apply our rules to the whole graph. But in some cases, we want to restrict our validation. Let's say we're working on a 200 million nodes graph, and I'm working incrementally. So I've just added in the last batch 2 nodes. Well, I can say, well, validate only the recently added portion. So in this case, I could say, okay, don't validate the whole graph, just restrict yourself to, in this case, again, I'm identifying them by ID. We're fixing that to get the complete ID. But basically, we can provide a list of nodes, a node set. And like this, we reduce the validation to a couple of them. So I'm saying validate only nodes 5 and 6. And if I do that, what would happen is exactly the same. So the same kind of rules are applied, but they're applied to a smaller set. And we would get results that are only applicable to that subset. You might say, hey, there's, so that's, and we can now see the result, and we only have things for 5 and 6, obviously. So that's, useful elements to kind of control which parts of the graph you validate, as opposed to the whole thing. I didn't touch very much on the details, but I describe how you can be very granular and express subsets of the graphs to define to which group of nodes a particular constraint applies, and that's I leave people to play a little bit with it and use it. But that's what I had for today. I hope that kind of tells the story and gives a good example. The code will go, of course, as always, into the GitHub repository. But that was it.
That was great. No, thank you very much, Jesus. One question before you go is, if you have a rule, maybe you come up with a rule that isn't covered here in your examples. Is there a possibility to add add something yourself, or how do you get to?
You mean like keep adding rules dynamically? So because you saw how I could change the existing ones. So in the same way, I can add new ones. So this is a dynamic set. And this is entirely controlled by you. So that's the thing. I would expect that as part of the process of building your graph or having your graph evolve over time, this collection of constraints or shapes will evolve, right? So some will be added, some will be removed, and this is entirely dynamic. So you will be able to to change that over time and to keep that list tracked version, like we were saying before. But yeah, that's meant to be dynamic and to change over time.
Okay, super. Cool. So that was very interesting. Thank you very much, Jesus. Quickly, to wrap up for today, I'd like to mention, obviously, Road to Nodes. It kicks off on the 5th of March. So that's in 2 days' time, on Thursday this week, with an intro to Gen AI with Neo4j by Martin. So it's going to be great. Join this one, or join Nodes in general, which happens on the 15th of April. We're wrapping up with Road to Nodes now, and 15th of April. Agenda is now live as well. So if you want to check it out, that's why I'm wearing the inaugural Nodes shirt. And yeah, if you want to know more and want to see more, check out the Graph Academy with interesting courses. Play with Aura free, and then obviously all the code and all the details for today's session, all the other sessions are on the GitHub repo. So if you want to play yourself with any of this, what Jesus showed today, do that. Let us know how it goes. If you have any feedback, any comments, as always, put it in the YouTube comment on this video, or let us know by tagging us in a social media post on your preferred platform.
Excellent.
And with that, thank you all for watching. Thank you, Jesus, for taking the time and for the demo today. And I guess I'll see you next month.
Pleasure. And I'll see you in a few weeks. So looking forward to the next one. Thank you, everyone. Thanks, Alex.
Thank you. Bye-bye.
Yes.